NENOMATICA, where mathematics meets YouTube excellence. Welcome to our mathematics lesson. Today, we will explore an interesting property related to the roots of a cubic equation. Let's begin with the proposition. If the roots of the equation ax cubed plus bx squared plus cx plus d equals 0 are members of z, the set of integers, then the constant term d is divisible by each of the roots of the equation. Note that we are assuming a equals 1. Now, let's prove this statement. We'll show that if x1, x2, and x3 are real roots of the cubic equation, ax cubed plus bx squared plus cx plus d equals 0, then the product x1 times x2 times x3 equals negative d over a. Since we've established that x1, x2, and x3 are members of z, the set of integers, and since it equals 1, we can deduce that x1 times x2 times x3 equals negative d. This means that if it equals 1, then the product of the roots x1, x2, and x3 equals negative d. Therefore, the constant term d is divisible by each of the numbers x1, x2, and x3. In other words, the roots of the equation are divisors of the constant term d. Let's illustrate this with a simple example. Suppose we have the cubic equation x cubed minus 6x squared plus 11x minus 6 equals 0. Here, a equals 1, b equals negative 6, c equals 11, and d equals negative 6. The equation can be factorized as x minus 1 times x minus 2 times x minus 3 equals 0. So the roots are x equals 1, x equals 2, and x equals 3. We can verify that the constant term d equals negative 6 is divisible by each of the roots. Negative 6 divided by 1 equals negative 6, negative 6 divided by 2 equals negative 3, and negative 6 divided by 3 equals negative 2. All are integers, confirming our theorem. Let's visualize this property. Here is a visual representation of our cubic equation, whose roots are all integers. The x-intercepts of the curve correspond to the roots of the equation. As we've proven, each of these integer roots is a divisor of the constant term d. In summary, we've proven that if the roots of a cubic equation, ax cubed plus bx squared plus cx plus d equals 0 are integers, and if it equals 1, then the constant term d is divisible by each of the roots. This property has important applications in finding the rational roots of polynomial equations and in number theory. Let's solve the cubic equation x cubed minus 5x squared minus 4x plus 20 equals 0. If the roots of this equation are members of the set z, integers, we need to find these roots. Let's start by using the rational root theorem. This theorem states that if p over q is a rational root of a polynomial with integer coefficients, then p is a factor of the constant term and q is a factor of the leading coefficient. In our equation, the constant term is 20 and the leading coefficient is 1. So, the possible rational roots are the factors of 20 divided by the factors of 1. Since the factors of 20 are plus or minus 1, 2, 4, 5, 10, and 20, and the factors of 1 are just 1, the possible rational roots are plus or minus 1, 2, 4, 5, 10, and 20. Let's substitute x equals 2 into our original equation to see if it's a root. When x equals 2, we get 2 cubed minus 5 times 2 squared minus 4 times 2 plus 20 equals 8 minus 20 minus 8 plus 20 equals 0. So x equals 2 is a root of our equation. Now, let's use the factor theorem. Since x equals 2 is a root, x minus 2 is a factor of our polynomial. We can use synthetic division or the result from the factor theorem formula to find the quotient when we divide our original polynomial by x minus 2. According to the factor theorem, if x equals lambda is a root of the polynomial p of x, then x minus lambda is a factor of p of x. The formula tells us that if x equals lambda is a root of the cubic equation, ax cubed plus bx squared plus cx plus d equals 0, then x lambda times ax squared plus a lambda plus b, x plus a lambda squared plus b lambda plus c, equals ax cubed plus bx squared plus cx plus d. We can solve this quadratic equation by factoring. Let's find two numbers whose product is negative 10 and whose sum is negative 3. The numbers negative 5 and positive 2 work because negative 5 times positive 2 equals negative 10, and negative 5 plus 2 equals negative 3. So the quadratic factors as x plus 2, x5 equals 0, therefore, x equals negative 2 or x equals 5. Now we can combine all our findings. the cubic equation x cubed minus 5x squared minus 4x plus 20 equals 0 factors as x2, x plus 2, x5 equals 0. Therefore, the three roots of the equation are x equals 2, x equals negative 2, and x equals 5. Let's verify that these are indeed integer roots as required by the problem. Since 2, negative 2, and 5 are all integers, they satisfy our condition that the roots must be members of the set Z. Let's summarize what we've learned. First, we used the rational root theorem to find possible rational roots. Then we tested x equals 2 and found it was a root. Using the factor theorem, we factored the cubic as x2 times a quadratic. Finally, we factored the quadratic to find the remaining roots x equals negative 2 and x equals 5. Direct hit these techniques are powerful tools for solving polynomial equations, especially when the roots are integers or rational numbers. Light bulb, remember, the rational root theorem gives us candidates to test, and the factor theorem lets us reduce the problem once we find a root. Let's start by examining our equation. First, let's look at the constant term of our cubic equation. The constant term is 12. To use the factor method, we need to find the possible factors of this constant term. The divisors of 12 are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. Now, the question indicates that x equals 2 is one of the roots of the equation. Let's verify this by substituting x equals 2 into our cubic equation. Now that we've confirmed x equals 2 is a root, we know that x minus 2 is a factor of our cubic equation. According to the algorithm shown in the reference material, we can use a factoring approach. If x equals lambda is a root of the cubic equation, ax cubed plus bx squared plus cx plus d equals 0, then the equation can be written as open parenthesis x minus lambda close parenthesis times open bracket ax squared plus open parenthesis a lambda plus b close parenthesis x plus a lambda squared plus b lambda plus c close bracket equals 0. Let's apply this factorization to our equation. Since x equals 2 is a root, we can factor our equation as open parenthesis x minus 2 close parenthesis times open bracket some quadratic expression close bracket equals 0. Using our formula, and noting that it equals 1, b equals negative 3, c equals negative 4, and d equals 12 in our original cubic equation, we get open parenthesis x minus 2 close parenthesis times open bracket x squared plus open parenthesis 1 times 2 plus negative 3 close parenthesis x plus 1 times 2 squared plus negative 3 times 2 plus negative 4 close bracket equals 0. Simplifying, we get open parenthesis x minus 2 close parenthesis times open bracket x squared minus x minus 6 close bracket equals 0. Now, we need to solve the quadratic expression x squared minus x minus 6 equals 0. For this, we can use the quadratic formula or factoring. Let's try factoring it by finding two numbers whose product is negative 6 and whose sum is negative 1. The factors of 6 are 1 and 6 and 2 and 3. Testing the sums. 1 minus 6 equals negative 5 and negative 1, whereas 2 minus 3 equals negative 1. So the numbers we need are 2 and negative 3. This means we can factorize the quadratic as open parenthesis x minus 3 close parenthesis times open parenthesis x plus 2 close parenthesis. Now that we have fully factorized our cubic equation, we can write it as open parenthesis x minus 2 close parenthesis times open parenthesis x minus 3 close parenthesis times open parenthesis x plus 2 close parenthesis equals 0. Setting each factor equal to 0, we get our three solutions. X equals 2, x equals 3, and x equals negative 2. Therefore, the roots of the cubic equation x cubed minus 3x squared minus 4x plus 12 equals 0 are x equals negative 2, x equals 2, and x equals 3. Let's summarize what we've learned. First, we use the factor theorem to identify that x minus 2 is a factor of our cubic equation, since x equals 2 is a root. Then, we use the factorization formula for cubic equations to express the equation as open parenthesis x minus 2 close parenthesis times a quadratic factor. Next, we factorize the quadratic expression into open parenthesis x minus 3 close parenthesis times open parenthesis x plus 2 close parenthesis. Finally, we found all three roots of the cubic equation x equals negative 2, x equals 2, and x equals 3. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.